Hi guys, so today we're going to be talking about binomial experiments. Before we get started with example 1, let's take a look at our book. So we can use the binomial theorem, which we've done previously, to find probabilities in certain situations where there are two possible outcomes. So there are 5 possible ways of getting 4 questions right and 1 question wrong. Right? And they're shown here on the right? So there's 5 questions here. So it's possible that you got the first one wrong and the other one's right, or it could be you got the second one wrong and the rest are right, the third one wrong and the rest are right, the fourth one wrong and the rest of them right, or the fifth one wrong and the rest of them right. Okay. This chart, right, shows the combinations of those 5 things taken 4 at a time. Or another way of seeing it is choosing, there's 5 questions and 4 of them are right. Okay? So what we can do is the terms of the binomial expansion of r plus w to the 5th can be used to find the probabilities of each combination of right and wrong answer. Right? So we're looking for 4r and 1w, and so that's here. Right? And that's where the 5 is. Right? So note, choosing 5 rights, all right, there's only 1 possibility, right? So 5 ways, the 5 here, 5 ways to get 4 right and 1 wrong, 10 ways to get 3 right and 2 wrong, 10 ways to get 2 right and 3 wrong, 5 ways to get 1 right and 4 wrong, and 1 way to get all of them wrong, okay? The other way we can see it is with this combination, right? We saw that with our binomial theorem, okay? So the probability of getting a question right that you guessed on is 1 out of 4. Okay? So the probability of getting the question wrong is 3 out of 4. Okay? So to find the probability of getting 4 questions right and 1 question wrong, you substitute 1/4 for R and 3/4 for W. Okay? In the term 5R to the 4th W. So then plugging it in for R and then W, you get this. So the probability of getting exactly 4 questions correct, provided that you're guessing, right? Obviously, if you actually knew the answers, the probability of you getting right is higher, right? Or if you think you know, etc., right? So this is if you're completely guessing, right? So the probability of getting exactly 4 questions correct, if you're completely guessing, is 15 over 1,024, or about 1.5%. Okay. So that's going to take us to example 1. Okay. So here, we're talking about if a family has 4 children, what is the probability that they have 3 boys and 1 girl? Okay. So there's 2 possible outcomes for a gender, right? For a boy or a girl. The probability of boy is 1/2. Probability of girl is 1/2, right? So again, scientifically, we know that based off of genetics and things like that, or even history, that could affect these probabilities. But generally, in this simple vacuum of our math textbook math class, we think of it as 50-50. Okay. So probability of boy is 1/2, probability of girl is 1/2. Okay. And since we're talking about 4 children, then we want b plus g to the 4th, right? So if you remember that expansion, okay. And then whether we're using the binomial theorem, b to the 4th plus 4b cubed g, right? So this is so remember, this is 4c1, 4c2, 4c0, 4c1, 4c2 is 6. And then 4c3 is 4 again. Cubed, and then 4c4, there's only one option, and that's just g to the 4th. Okay. Right, so think back to our binomial theorem. Again, 4, so 4c0, 4c1, 4c2, 4c3, 4c4. Note B's are going down 4, 3, 2, 1. G's are going up. G to the 0, G to the 1, second, third, fourth. Okay. So then, if we want 3 boys and 1 girl, we're looking at this. Right. 3 boys, 1 girl. Okay. So then, the probability of 3 boys and a girl are going to be 4. And then B is 1/2, so 1/2 to the 3rd times 1/2. Okay. So then when you multiply all of that, that becomes 1/4. Okay. So the probability that they'll have 3 boys and 1 girl is 1/4, or we know that as 0.25 or 25%. So why don't you try CYP1, and then once you're done, come check answer. Okay, you should have gotten 15/64, or 0.234375, which is approximately 23%. If you got that right, you can move on to the next example. If not, here is your explanation. Okay. So here we're flipping a coin 6 times. We want to know the probability that the coin lands heads up 4 times and tails up 2 times. Okay? So the probability of rolling a heads is 1/2, or flipping a heads is 1/2, and the probability of flipping a tails is 1/2. Okay, so that's why H is 1/2 and T is 1/2. Okay. So here our binomial thing is heads or tails, right? So it's H plus T, and since we're flipping it 6 times to the 6th power, okay, this is the binomial expansion for it. Okay. And then here, H to the 4th, T squared, right? Head 4 times, tails 2 times, so I want this one here. So that's why we see 15. Heads is 1/2 to the 4th, right? Heads 1/2 to the 4th. Tails 1/2 to the 2nd. Multiply that together, that gives me 15/64, which is which is approximately 23%. Okay? Okay, in our last example, we're going to be talking about binomial experiments. Okay? So problems like example 1 that can be solved using binomial expansion are known as binomial experiments. Okay? So a binomial experiment exists if and only if all of these things happen. Okay? So first of all, there has to be exactly 2 possible outcomes for each trial, right? So if we think about the whole family thing, it's either going to be a boy or a girl, right? 2 possible outcomes. When we think about flipping a coin, it's either going to be a heads or a tails. Okay? Secondly, there's a fixed number of trials, quote unquote, right? With a family example, there's 4. There's 4 children. Okay? And then with the flipping of the coin, right, there was 6 flips. Okay? The trials are independent. So the family one isn't a good example of this because technically we know from science that based on your genetics and things like that, you can actually be predisposed or more likely to have a boy or a girl. So it's not great, but generally we kind of think about it in our vacuum of stuff that what happened before doesn't affect what happens later, right? Or flipping a coin, right? Just because I flipped a tails next time doesn't mean that I'm more likely to flip a tails or less likely to flip a tails if everything is even, okay? And then the probabilities for each trial are the same, right? So it doesn't mean that they're independent, right? So it doesn't change what happens next, okay? So with that in mind, let's look at example 2. Okay? So suppose that when hockey star Martin St. Louis takes a shot, he has a 1/7 probability of scoring a goal. Okay? He takes 6 shots in the game. What is the probability that he will score exactly 2 goals? All right? So we want the probability of 2 goals. Right? So this is a binomial experiment because there are 2 outcomes. It's either a goal or not a goal. There's a fixed number of trials. We know that he's taking 6 shots in the game. Right? The trials are independent. Generally, things aren't going to change. Right? Just because he missed a shot once, ideally it wouldn't he wouldn't miss a shot again, although technically we also know in sports there are things, you can get in your head and then you can be a little bit nervous and then that might change the probability of you. But in the perfect world, like him making the shot, missing the shot or making the shot doesn't affect him later. Okay, and then the probability for each trial is that same. It's that 1/7. Okay, so the probability then, okay, so we know he's taking 6 shots, okay, and we want exactly 2 goals, okay. The probability of his success is 1/7, and we're hoping there's 2 of them, okay. So if that's the probability of his success, then his failure is 6/7. Right? And so if 2 of them are successes, that means that 4 of the 6 here would be failures. Okay? So then let's figure out what 6C2 is. 6C2 is 15. Okay? And then 15 times 1/7 squared times 6/7 to the 4th is 19440 over 117,649. Okay. And then if I enter that into my calculator to find the actual decimal, this is approximately 0.16524, or approximately 17%. So the probability in 6 shots that he'll score exactly 2 goals is approximately 17%. Okay? So the next one asks for the probability that he will score at least 2 goals. Okay? So one way we can do it is probability of 2 plus probability of 3 plus probability of 4 plus probability of 5 plus probability of 6, or it would be easier, right, to just subtract 1 minus the probability of no goals and the probability of 1 goal. Right? It's easier to just have to really do 2 of these rather than 2, 3, 4, 5, and 6. Okay, so let's go. So probability of 0 goals. That means of the 6 shots, 0 of them go in. Okay. That means of the success, the probability of success is 1/7, right? There's 0 of those. However, of the failures, which is 6/7, there's 6 of them. Okay. Minus the probability of 1 goal, so 6, and we're choosing 1. Okay. Of the successes, of the 1/7, 1. Of the failures, 6/7 is 5. Okay. So then let's simplify this. So 6C0, so this is 1. This is 1 as well. 1 times 1 is just 1. So we just need to do 6/7 to the 4th, which gives me 46656 over 117,649. Okay, and then 6C1 is 6 times 1/7. So the first is just 1/7 times 6/7 to the 5th power. Okay. And then that will give us 46656 over 117,649. Okay. And then when we do that, this gives us 24337. 24337 over 117,649. And then that is approximately 0.20686, or approximately 21%. And there you go. So why don't you try CYP 2A and 2B on your own, and then come check your answer when you're done. Okay, so the probability that this basketball player makes 2 free throws, exactly 2, is 45 over 512, which is approximately 0.08789, which is approximately 9%. The probability that he'll make at least 2 free throws is 63 over 64, or 0.984375, which is approximately 98%. If you got that right, you can get started on your homework. If not, here is your explanation. Okay, so he has a 75% success rate, which means his failure rate is 25%. So probability of 2 free throws, if he's making 5 of them, he's going to take 5 of them, and we want 2 free throws, so that's 5C2 for combination. Okay. Of his success, 0.75, he's going to make 2 of them, so 0.75 to the second power. And then of his failure, 0.25, there's going to be 3 of them, so 0.25 to the third. And then simplify that, and this is what you get. Okay. So probability to make at least 2 free throws, so what we want is either 2, 3, 4, or 5. Instead of adding the probability of 2, 3, 4, and 5, one way we can do it is take away, out of the 100%, take away the probability of 0 and 1. Okay, so that's what's happening here. So for the probability of 0, that means of the 5 shots, 0 of them go in. So of the success here, 0 of them. Of the failures, 5 of them. And that simplifies to this. Okay. Then for the probability of 1, that means of the 5 shots, only 1 goes in. Okay. So of the success, there's 1. And of the failures, that's 4. That simplifies to this. Okay. And so this then simplifies to 63 over 64, which is this as a decimal and about this as a percentage. Okay. So that's it for today. Have a great rest of the day. Bye, guys.